Welcome back everyone. So, in the last lecture, we have seen how to find the Laplace transform of the periodic functions and the different examples based on it. Let us quickly go through the solution of the last question of previous lecture which I have given you as an exercise. So, we have to find the Laplace transform of the given periodic waveform. Now, look carefully. This waveform is addition of two functions. From 0 to 1, the value of ft is 1. And from 1 to 2, the value of the function ft is minus x plus 2. You can easily find out this by using the equation of a straight line passing through 2 points from 1 1 to 2 0. So, we get our function ft as 1 for t greater than 0 and less than 1 and minus x plus 2 for t greater than 1 and less than 2. And as the function is repeating after every 2 time period, we can also write ft equal to ft plus 2. Now, by applying the property of Laplace transform of periodic functions, we can write Laplace transform of ft as 1 by 1 minus e raised to the power minus 2s into integral 0 to 1 e raised to the power minus st into 1 dt plus integral 0 to 2 e raised to the power minus st into minus x plus 2 dt. So, now on solving the integral, we get the integral of e raised to the power minus st as e raised to the power minus st by minus s from limit 0 to 1. And for finding the integral of e raised to the power minus st into minus x plus 2, we can use integration by parts. So, by integration by parts, we get minus x plus 2 into e raised to the power minus st by minus s, limit from 1 to 2, minus integral 1 to 2 e raised to the power minus st by minus s into dt. And on solving this and by putting the limits, we get the answer as 1 by 1 minus e raised to the power minus 2s into 1 by s minus e raised to the power minus s by s square plus e raised to the power minus 2s by s square. So, till now, we have seen various different properties of the Laplace transform and the examples based on it. Now, in this lecture, we will see the application of the Laplace transforms in solving the integrals. To understand this, let us go through some examples. Example 1. Using Laplace transform, find the value of integral 0 to infinity t into e raised to the power minus 4t into sin t dt. So, here we have to find the integration of the function, not the Laplace transform. Let's see how we can find this. So, as we know that the Laplace transform of sin t is 1 by s square plus 1. So, the Laplace transform of t into sin t we can find out by using multiplication by t property. That is minus d by ds of 1 by s square plus 1. Now, see the Laplace transform of t into sin t by the basic definition we can write it as integral 0 to infinity e raised to the power minus st into t into sin t dt, which is equal to 2s by s square plus 1 whole square, that we can find out by solving the differentiation. So, now if we replace s by 4, that is, if we put s equal to 4 in the above equation, we get integral 0 to infinity e raised to the power minus 4t into t sin t dt equal to 2 into 4 by 4 square plus 1 whole square, which is equal to 8 by 289. So, you have seen how easily we have calculated the integration by using the Laplace transform. Whereas, if we had calculated the same integration by the basic integration process, it would have been much longer and tedious one. Let us take some more examples for better understanding. Example: using Laplace transform, find the value of integral 0 to infinity e raised to the power minus t minus e raised to the power minus 4t by t dt. Let us check the solution. As we know that the Laplace transform of e raised to the power minus t is 1 by s plus 1, and Laplace transform of e raised to the power minus 4t is 1 by s plus 4. So, what will be the Laplace transform of e raised to the power minus t minus e raised to the power minus 4t by t? It will be integral s to infinity 1 by s plus 1 minus 1 by s plus 4 ds by using division property of Laplace transform. So, on solving the integration, we get Laplace transform of ft as log s plus 1 minus log s plus 4 from limit s to infinity, which we can also write it as log s plus 1 by s plus 4 from limit s to infinity. And by putting the limits, we get it as log s plus 4 by s plus 1. Now, the Laplace transform of ft, that is e raised to the power minus t minus e raised to the power minus 4t by t. We can also write it as integral 0 to infinity e raised to the power minus st into e raised to the power minus t minus e raised to the power minus 4t by t dt. So, our equation becomes integral 0 to infinity e raised to the power minus st into e raised to the power minus t minus e raised to the power minus 4t by t dt equal to log s plus 4 by s plus 1. Now, we have to find the integration of integral 0 to infinity e raised to the power minus t minus e raised to the power minus 4t by t dt, as we do not want e raised to the power minus st term in our integration. So, if we put s equal to 0 in this equation, we get our desired result. That is integral 0 to infinity e raised to the power minus t minus e raised to the power minus 4t by t dt equal to log 4. Okay, so let us take one more example. Using Laplace transform, find the value of integral 0 to infinity e raised to the power minus t into sin t by t dt, and also integral 0 to infinity sin t by t dt. Okay, so let's do it. As we know that Laplace transform of sin t by t is equal to integral s to infinity 1 by s square plus 1 ds by division by t property. On solving the integral, we get the Laplace transform of sin t by t as tan inverse s limit from s to infinity, and the Laplace transform of sin t by t by the basic definition will be integral 0 to infinity e raised to the power minus st into sin t by t dt. So, we can write integral 0 to infinity e raised to the power minus st into sin t by t dt equal to pi by 2 minus tan inverse s by substituting the limits to the right hand side. Now, by putting s equal to 1, we get integral 0 to infinity e raised to the power minus t into sin t by t dt equal to pi by 2 minus tan inverse 1. And what is tan inverse 1? It is pi by 4. So, integral 0 to infinity e raised to the power minus t into sin t by t dt is equal to, we get pi by 2 minus pi by 4, that is pi by 4. Similarly, if we put s equal to 0 in the same equation 1, we get integral 0 to infinity sin t by t dt equal to pi by 2 minus tan inverse 0, which is equal to pi by 2, as tan inverse 0 is 0. So, with the help of these examples, now I think that you have understood that how to use the Laplace transform in solving the integrals, which are although very tedious and time consuming if done through normal integration process.